Hello, everyone. Thanks to all of you for attending the Heidelberg AI event today. This is the first event this year, and we hope we will have some more this year, and we're looking really forward. And we have a really nice act today for you. We would like to give a special thank you to our sponsors, which is the Medical Image Computing Division at the Dataset and the Interactive Machine Learning Group, which is led by Dr. Paul Jäger, and the Medical Image Computing Division is led by Professor Dr. Klaus Meyer-Hein. And also, we would like to give a special thanks to our other sponsors, and especially the German Cancer Research Center for giving us the facilities to host these events, and also Helmut's Imaging in general. Our other sponsors are Alice and the Data Science Seminar, with which we also cooperate. So this event is actually a special event because this event is held because all of you requested it. So at the last event, the most requested talk was, hey, let's do something about stable diffusion. They are actually from Heidelberg, so we could promote our local AI heroes who make open source projects available for everyone, which compete with DALI, which is a closed source project. And it is actually quite hard to get into contact with the authors of this work because they blocked all social media because they just get overwhelmed by everybody requesting something of them. But at the last event, we met someone who was able to give us their private email address, and so we contacted them, or we contacted Robin. And we wrote him, and we were not sure whether he would attend or whether he would even have time to have an event here. But it turned out that his first contact with the machine learning community was here at an Heidelberg AI event. And it was here that he got into contact with Professor Ommer, which led to his master thesis and also his PhD. So we are very glad that he accepted it. And now will give a talk for us. And if you ever wonder who you really have to thank for stable diffusion, it's probably Heidelberg AI. So let's talk about Robin for a bit. He did his studies here in Heidelberg, and he studied physics. And then he did his master's at Professor Ommer's lab, and did work there with all types of generative models, and also worked with normalizing flows, and did work with also other, collaborated there with other people, and resulting in a lot of very good research. And now he's a PhD student and moved with Professor Ommer to the LMU, and is also a principal researcher at Stability AI, which is working to get stable diffusion into the hands of as many people as possible and to wrap it in an easy manner for people to access it. Without further ado, I would hand the talk to our speaker.
Yeah, thank you for the very nice introduction. It's actually true. It's kind of crazy to be here like 7 years or 6 years after my first Heidelberg AI event, where I first got into contact with AI. So yeah, I remember sitting there in the lecture hall above. I think it was a talk about reinforcement learning, which was super hyped at this time. Someone from OpenAI came, so really cool. And it's a bit surreal to be invited here today, but it's also very cool. So thank you very much. I'm going to talk about stable diffusion, and I'm also going to talk about the research that we did as a in the computer vision group here in Heidelberg, and then also in Munich after the group moved. And I'm going to talk about this research that is kind of underlying for stable diffusion. And I would also like to talk about some of its applications, fine-tuning techniques, and where this might go in the future. Okay, so I think most of you have probably heard the term generative model or generative AI, at least in the past months. So especially given the latest hype about ChatGPT. But what does generative model actually mean? So let's imagine an image that corresponds to this text prompt here. An image of an astronaut riding a horse. And these are a few suggestions that are created by Stable Diffusion. And every one of you probably had like a different image in mind. And I think this nicely illustrates that the creation of new images, given a certain text input, is like an unspecified or one-to-many problem. And there exist arbitrarily many possible astronauts riding horses in different styles or in different poses or contexts, which would all be aligned with the text prompt, an image of an astronaut riding a horse. Some of them are more likely, and others are not. And learning this underlying distribution of these possible outputs is, in essence, what a generative model does. And that means that given a generative model, we sample a possible outcome from it, and we thereby create new content. So like these images of these astronauts, which did not exist before. And when I say that a generative model learns the underlying distribution of the data, we need to provide some examples from which the model can actually learn. And ideally, these are examples of what our visual world looks like, and we would call them samples from the true data distribution. And we now create a generative model that can be trained to generate images from scratch. And this model is represented by a large neural network, and the resulting newly created images are referred to as samples from the model. And more formally, we can think of our training data set as samples taken from this true data distribution. And the blue region here in this example image illustrates the part of the image space that is most likely to contain real images. And these black dots here represent data points, which in the case of an image data set are images. And by evaluating the output of a neural network, which actually is our generative model, here in yellow, our model produces a generated distribution, p hat in green. And this network has parameters, and modifying these parameters, which we basically do through stochastic gradient descent, will adjust this generated distribution of images. And our aim when training a generative model is to find the parameters that produce a distribution that closely matches the true data distribution. And since these will come up later in the talk again, I would like to very briefly introduce 3 types of generative models that have been very successful with images recently. This is not a complete list, and there are other models such as variational autoencoders and normalizing flows, which could potentially make a comeback for image synthesis in the future. But right now, these are the ones that work best. So the first is a GAN, or a generative adversarial network. And GANs formulate the training as a game between 2 separate networks. A generator network and a second network, a discriminator, which tries to classify samples from the generator as either real or fake. So as either coming from the true data distribution or coming from the model distribution. And every time that the discriminator actually notices a difference between the 2 distributions, the generator has to adjust its parameters to try to fool the discriminator. And in the end, ideally the outcome is that the discriminator is just randomly guessing, and the generator reproduces data from or produces data from the true data distribution. Then we have autoregressive models, and autoregressive models use the chain rule of probability to train a network that models the transitional distribution of every individual pixel given the previous pixels. So in this, to train this, we need to introduce some order for the pixels. So we could do something like unrolling an image from top left to bottom right, but we could also do other orders. This is kind of an arbitrary choice. And this approach is also very popular in natural language processing and is behind models such as ChatGPT. And finally, we have diffusion models. And diffusion models formulate the learning process as a form of iterative refinement. And they learn to denoise the training data from corrupted images on which Gaussian noise was applied. And I'll explain more on them later, but in essence, they work because they kind of introduce a hierarchy in this process and have like this denoising task from more simple noisy data representations, such as the ones close to the left, and also from the hard ones. So if you would predict directly from pure noise to the output, that's a very hard task. But by doing this iteratively, this is kind of what makes them actually good. Okay, but yeah, let's jump into text-to-image generative models. And the progress that this field in particular has made is extremely impressive. On the top, we see a few samples from very early models from 2015 that were based on RNNs or on GANs. And these produce like barely recognizable outputs, blobs at a low resolution of either 32 or 64 pixels. And on the bottom, we have outputs from DALL-E 2 and from Stable Diffusion, which were both introduced last year in summer, and which reach megapixel quality and very good generalization. And since both my master's and PhD thesis here in Heidelberg were mainly focused on image generation, it's quite exciting to actually see this progress. And I now briefly want to explain what we as a research lab actually contributed to this field. So when we were working with these generative models, there were already like high quality image models around. Maybe some of you know StyleGAN or StyleGAN 2. So the most successful models were generative adversarial networks. But they were kind of restricted to simple domains or more restricted data sets, such as this toy data set, Cypher10, but also real photographs, but these were like portrait photographs or portraits of animals, like the ones that you can see here. On these restricted data sets, generative adversarial networks or StyleGAN in particular works really well. But we asked ourselves, is it possible to achieve quality like this, but for a very diverse data set, for one which where images would kind of represent the real world, right? So depict various scenes, various styles, objects at different scales and interactions, and so on. And yeah, these are kind of images like the ones that are shown on this slide here. These images are from the very diverse Open Images dataset. And this dataset includes humans, animals, non-living objects, cartoons, and so on. But before I present our approaches to this specific task, I would also like to discuss the question of what actually makes up a realistic image and a realistic composition in an image. And I would argue that a realistic image with a realistic composition gets two things right. First is the local structure. So in the case of this image here, this includes the textures of the giraffe's fur, or the grass on the ground, or the leaves in the trees, and so on. And then there's also the global structure in the image that our model needs to get right. And this includes things like perspective and that distant parts of objects are consistent. We need a consistent illumination, and the objects need to realistically interact with each other. So for example, the giraffe bending down to eat the grass here. And these things require a model that acts globally and which can actually model these global interactions, the perspective, and the texture rendering. And our first approach to this, to build like this knowledge or this intuition into a generative model, was published in a paper, Taming Transformers for High-Resolution Image Synthesis. And I would like to briefly mention this here because it shares the motivation with the two-stage approach that is also used in Stable Diffusion. Okay, so why would we use transformers, as the paper title suggests? So, as I just discussed, we wanted to train a model which can essentially capture the generative distribution of this very diverse data set like open images. And when we were working on the paper, on the model, Transformers such as GPT-3 were already established and were used in natural language processing to solve very complex, diverse language modeling tasks. And the training objective for them is, or like a common training objective for them is next token prediction, which is formulated as this autoregressive factorization of the data distribution that I mentioned earlier. And this formulation also offers a few advantages over implicit approaches such as generative adversarial networks. And the first is that the likelihood that these models actually offer can be evaluated exactly, which is not the case for GANs. And this actually enables a straightforward model comparison. So you can actually compute this value and just say this model has produces a lower likelihood than the other one, which might be better. Then another advantage of that is that the training is very stable. So balancing this two-player game can be very hard. And training a likelihood model, and especially like an autoregressive likelihood model, is very stable. And the loss is very smooth. And next reason is that this likelihood-based formulation actually turns to learn a model which does not suffer from something that's called mode collapse. It covers the whole data distribution. But on the downside, this also introduces a disadvantage because covering the whole data distribution means that this also includes or it includes all the details in the image or in the input space. For images, these are like imperceptible high-frequency details, which can cause problem when the goal in the end is to generate realistic images. And this is a problem that has been described as something or as getting lost in the details. And it's a typical shortcoming when we want to apply autoregressive models directly in pixel space. And in essence, the problem is that these models, when trained in pixel space, they spend too much capacity on modeling these high-frequency details in the images. So capacity is kind of wasted. And in a nutshell, this means that the space in which we measure the likelihood and in which the model is trained matters. Okay, so I'll try to explain this again one more time with this example here, an image of a squirrel. So our goal is image synthesis, right? So we want to generate something like this. And for that, it's important that we capture the global structure and the global pose and a realistic kind of physics and so on. But we are usually not interested in modeling these exact local structures like the texture of the fur. What we're interested in is that it looks like realistic fur, but we are not interested in the precise interaction and locations of the individual hairs. And using this insight can really help to train better generative models of images, because if we can get rid of these imperceptible high-frequency details in a first stage, our generative model does not need to learn the distribution over them, and thereby it does not need to waste the capacity on these details that we, as kind of consumers of the output of the model in the end, will not perceive anyways. Okay, so the approach that we presented was fairly straightforward. As I just mentioned, in order to do this two-stage generative modeling, you usually have to compress the input data into, you have to compress the input data quite a bit. And especially if you're compute restricted, like we were at the research lab here at the university, you would need to compress quite a bit because transformers do not really computationally scale well when we increase the data dimensionality. So, and our main goal was to avoid modeling these fine high-frequency details that I talked about. And we therefore introduced this model we called VQGAN. And this builds on previous work called VQBAE. And there an image is represented as a sequence of entries from a learned codebook. And more precisely, we used this formulation of VQBAE, which relied on straight-through gradient estimation and vector quantization to simultaneously learn like the encoder and decoder modules to map an input image to a discrete representation and the codebook into which the image is quantized in the latent space. And what we can do with this model is that after training, it produces a compact, discrete representation of an input image. So a typical scenario is that we have an input image of size 256 by 256 pixels. and we put it into this model, and then we get like a latent code of size 16 by 16, and then we can kind of choose the codebook size as a hyperparameter. Typical values would be something like 1024 or 8192. Oh yeah, sorry. Yeah, but if we would only, so the goal is to generate high resolution, crisp, sharp images. And if we would only rely on VQ-VAE in the standard formulation, then we have a problem, because on the one hand, we want to compress as much as possible, but on the other hand, we want to have this crisp reconstructions from the model. And if we just do the VQ-VAE formulation, which is based on a pixel-wise reconstruction, then this will lead to a trade-off which produces blurry reconstructions. So to overcome this, we kind of introduced two things. First is we included a perceptual loss to guide the reconstruction, but using this alone would still introduce artifacts. And then we introduced, this is the important part of it, it's also why it's called VQ-GAN, a local discriminator. And this local discriminator is applied on the outputs of this autoencoding pipeline. So on the outputs of the decoder here, on the reconstructions, and it makes sure that the model kind of commits to local realism. So the discriminator is applied patch-wise, and yeah, we then favor realism over perfect reconstruction. And yeah, this means that the total loss of this model is actually a combination of the VQ loss, which we need to learn the codebook, the reconstruction loss, and also this adversarial loss. And initially, we found it super difficult to correctly weigh these terms and get like a stable training. And this is why we introduced like a more dynamic strategy by calculating this adaptive weight that we applied to the adversarial loss. And basically what this weight does is that the contribution of the adversarial loss is decreased as soon as the gradient of the GAN loss is larger than the one of the reconstruction loss. And another important bit to get this really going is that we actually warm up the training by training with reconstruction loss first only, and then just tuning in the discriminator after a while, after the model has kind of already learned to what a reconstruction actually is. Okay, so let's look at some results from this model. And we can, as an illustration, consider the squirrel again. So for a standard discrete variation autoencoder like VQ-VAE or this one here, this is the one that was used with the DALL-E 1 model. The overall structure of the reconstruction is good, but local details are blurred out and the texture of the fur or of the stone is not crisp. So this is exactly this trade-off that I just mentioned. And when we instead train a VQ-GAN with the exact same latent capacity and the exact same latent size of the representation, we achieve very good reconstructions and simultaneously realistic-looking images. We can now use this to increase the compression even more. So this f equals 8 here means that an input image of size 256 by 256 is downsampled by a factor of 8. We have a representation of size 32 by 32. We can increase this compression ratio to 16, get a representation of size 16 by 16 in this case. And there still, the reconstruction looks realistic, but what we see is that it's kind of this trade-off that we make, that the reconstruction is not perfectly aligned with the input anymore, but it still looks like a realistic paw. Okay, so we have seen that this approach gives us the ability to reconstruct a given input with a decent level of realism, but this still does not give the full generative model, right? Because the only thing that we can do with this right now is to produce this discrete latent representation or reconstruct images from it, but we cannot generate new images. And what we now do is we actually come to the transformer training part. So we have a trained VQ-GAN, we have a data set in which we want to train the transformer. We fix the VQ-GAN, we simply pass all the training images through the VQ-GAN encoder, And then we get like this discrete representation. We can unroll it from top left to bottom right, but we can also choose any other order. And if we have 256 by 256 images, this is a 16 by 16 array. So we have a sequence of length 256, and on that sequence, we basically train a transformer on next token prediction, just like a classic language model. And we can make this a more flexible model by adding a conditioning, like a class label, or more interesting, a text prompt. So we can add text tokens, tokenized text, concatenated with the image representation, and then we get like a text-to-image model out of it. We actually did not do that in the first version of the paper because this is super expensive to train, and you need large-scale data. What we did was we applied this to these landscape images here that we scraped from Flickr, and the results were already at a high resolution, but still not like for very diverse data sets. So I'm actually thankful to Google that they demonstrated that this works. So they took this approach and published a paper last year in June called Party. And this is basically VQGAN plus transformer applied to text-to-image modeling. So they scaled this to a 20 billion parameter model and produced really good-looking results. They took a slightly different version of VQGAN, which is based on a more modern architecture, but in essence, it's exactly what I was just talking about. And yeah, another thing that was a bit surprising is that it actually turned out that this highly compressed latent representation from VQGAN was useful or suitable for a variety of other tasks. So one of them is single image optimization. And after we released VQGAN and then OpenAI released CLIP, I think a few weeks after, CLIP is a model which basically produces a similarity or predicts a similarity between an image and a text prompt or text caption. People used these models, plugged them together, and kind of optimized latent codes to match text prompts. This can be used as a way to also get like a text-to-image model. And this approach was at times very hyped in this online AI art community, and it produced a very unique style, like the one that for these two images here on the left. And this approach could also be used for text-driven style transfer. So given an input image, like this image of the bird here in the middle, you can use the same approach and optimize until you match a certain style. So this already works kind of well, but it's slow because it's single image-based optimization. Okay, so we were certainly not the only ones that were working on generative models, and while we did our work on VQGAN, another popular approach for image synthesis actually emerged or re-emerged, and of course I'm talking about diffusion models. Diffusion models were actually around for a while, so there was a paper in 2015, but they did not really catch on until 2020, until Jonathan Ho and AJ Jain published this paper on denoising diffusion probabilistic models, and they showed that these types of models work really well for class conditional or like for image synthesis on these face portrait data sets and for some other data sets. But in essence, it showed that this is actually a really valuable approach. And then lots of papers popped up which built on top of that paper. OpenAI published a paper, Diffusion Models Beat GANs on Image Synthesis, which set a new state of the art in class conditional image synthesis on ImageNet, which is kind of a difficult benchmark, or one of the most difficult benchmarks until then in image synthesis. But the downside of these models is that they were, like, how they were trained at this time was that they were trained directly in pixel space and require super large batch sizes. And this makes it really expensive and kind of limited access to this class of generative models. And this is on a high level the motivation that we had, or what we tried to tackle when we with our work on latent diffusion models. But before I jump to that work, I want to briefly explain what diffusion models actually do. Okay, and the basic idea here is that a denoising diffusion model should invert a Markov chain that gradually adds noise in the opposite direction of sampling to the signal until the signal is destroyed. And this means that the model consists of two parts, an encoder, which is called the diffusion process, and a decoder, which is called the denoising process. And the interesting part here about the encoder is, or about the diffusion process, is that it is fixed and it adds stepwise small amounts of Gaussian noise to the data until it finally approaches a standard normal distribution. And then the decoder basically learns to invert this process. And there exists different formalisms, either based on stochastic differential equations or on hierarchical latent variable models, which describe this approach and formalize it a bit. But I think it's actually not too important today. For us, it should be sufficient to know that a diffusion model can be interpreted as a sequence of denoising autoencoders in the simplest case. And diffusion models have a nice feature. They make this difficulty of training likelihood-based generative models that I already talked about with VQGAN, they make this directly visible. So for example, you can take a trained diffusion model and then plot the rate dispersion curves over different diffusion steps. We can then see that the majority of bits is allocated to details that are nearly imperceptible. And usually for a generative model of images, we're not interested in modeling these imperceptible details. We don't want to waste model capacity on them. This is equivalent to this motivation behind VQGAN. So very nice feature about diffusion models, and I think this is also what contributed a lot to their initial success, is that they can already account for that. By reweighting the contribution of the different diffusion steps in the optimization objective, we can explicitly get rid of these terms and arrive at what is often called the simple diffusion objective. And this simple diffusion objective implicitly undersamples steps which are perceptually irrelevant. But still, although diffusion models have this nice feature kind of built in, they still need to be trained and evaluated on pixel level, which makes both the training and the inference very expensive, especially inference because the model is iteratively applied until we arrive at a final image, a denoised image. And then, of course, coming from the VQGAN background, we asked ourselves, is this possible to find like a representation on which we can still diffusion model, which is still perceptually equivalent, but of a better computational complexity? And again, this is where like our two-stage approach comes in. And in this work on latent diffusion models, we experimented with a variety of autoencoders, which we always combined with this adversarial objective that I already talked about with VQGAN, learned the latent space, over which we then learned a diffusion prior in the second stage. And ideally, this approach would maintain all the advantages that diffusion models actually have, but at a reduced computational complexity. And this is an overview of the entire pipeline that we proposed in this paper. So this autoencoder can either be a VAE, variational autoencoder type model, with a very low Kullback-Leibler regularization on the latent space, or it could be a VQGAN. The most important part is that we have higher fidelity reconstructions guaranteed. And in the experiments with VQGAN, we kind of absorbed the quantization layer into the decoder and trained on pre-quantized latent codes. And we also designed this model to incorporate all kinds of conditioning informations. So these conditioning informations can, for example, be spatially aligned representations such as low resolution images. So if you have low resolution images, you can do upscaling. It could be semantic maps, semantic image synthesis, or, and this is then important for stable diffusion, text prompts. These are not like these, this is not a spatially aligned information, it's very abstract information, so we need to find a way of mapping this into the model. And typically, diffusion models for images are implemented as units. So to build this conditioning mechanism for text into the model, we modified the existing unit architectures. So this one was from OpenAI's class conditional model from that paper, Diffusion Models, Speed GANs, and Image Synthesis. And what we did is we added small transformer blocks into the unit. These are kind of illustrated with these QKV components in the unit there. And these transformer blocks themselves consist of self-attention, cross-attention, and feed forward. So these are fairly standard transformer blocks. And what we then have is that we have a kind of encoder-decoder architecture where the encoder is shared for all diffusion steps and all feature resolutions. And yeah, we have like a step-specific decoder. And for example, this encoder can be a standard transformer model or a standard transformer encoder, just like in natural language processing without masking, which first pre-processes a text sequence and then produces an output, like an embedding sequence. This embedding sequence is then mapped through cross-attention into the unit. Yeah, and when we first published a paper, we actually trained this text encoder jointly with the rest of the unit to learn a text-to-image model. But I now want to jump directly into Stable Diffusion and explain what we did there, so I'll skip that. When we had the chance to train Stable Diffusion, the main difference to Latent Diffusion, as we originally proposed it, is actually that we took some inspiration from a Google paper that was published in the meantime. And in the Google paper, they suggested to use pre-trained fixed text encoders, which worked really well. They did some experiments on using like large-scale pure text-based text encoders, or also the CLIP text encoder. So again, CLIP aligns or kind of learns to produce this similarity between images and text. Therefore, to do that, it needs a text encoder and it needs an image encoder. We just used the text encoder of that for these experiments, or also Google did that. And the advantage of CLIP is that it's super small model, like this VIT-L14 that I mentioned on the slide here has like 110 million parameters, which is really, really small in comparison to the standard text encoders. And our goal was to kind of train a model which is as lightweight as possible. And Google also did some experiments on the performance trade-offs between these different text encoders and kind of showed that CLIP actually works really well, and only the largest versions of the text encoders have a significant advantage. So this is why we thought, okay, let's just stick with the CLIP encoder, because this is good enough for our use case. What we also did is we did this progressive training. So we pre-trained Stable Diffusion on 256 by 256 pixel resolution, and then continued the training or fine-tuned the model in 512 by 512 images, fixed text encoder, as I just said. And yeah, maybe we can. Yeah. So the pre-training was the stage at 256 by 256 image resolution. We kind of fixed the batch size to 2048 and used 64 A100 GPUs for that. So that's not too expensive for that. And we trained on this large-scale dataset Lion2B. This is a open source dataset or openly available dataset which contains 2 billion or close to 2 billion image text pairs. And then in the next stage, we fine-tuned the model on higher resolution, and to kind of keep the batch size at 2048, we had to increase the numbers of GPUs that we use. So for this, we used 256. We then did a first stage where we trained this model for 200K steps on this high resolution data. And this model was actually used to or deployed in a Discord chat. And the outputs from that model were rated by users from that Discord bot. And these ratings were used to create they were kind of ratings on how beautiful an image is. And these ratings were used to create an aesthetic prediction model. This aesthetic prediction model was then kind of applied to Lion 2B. So there's kind of a feedback loop in here because we then filtered out images with a low aesthetic score as predicted by this model. We also filtered out low resolution images. So this is kind of a restricted subset of Lion 2B. I think around 60 to 70 million images only. Trained this for 500K steps, and then in the final part, we trained this for 200K steps more, where we, at a chance of 10%, dropped the text conditioning for something that's called classifier-free diffusion guidance. I'll mention that in a second. And the final model that we arrived at is if you store this at full precision, it's a 4.2 gigabyte checkpoint. So quite a lot of compression for this amount of data. These are some outputs from the model, which I did not create, but I just collected from Discord because other people are way better than me at doing this. This is kind of this classifier-free diffusion guidance that I just mentioned, and this is, I would say, the most important ingredient to really make this work. So this is kind of a cheat code that was introduced by a Google paper in also 1.5 years ago for conditional diffusion models, which also means text conditional diffusion models. And an intuitive explanation of what it does is that during the denoising process, it pushes the model away from an unspecific or an unconditional model output towards the conditioning signal. And this means that to actually implement that, we need to evaluate this unconditional model output. And this might seem to be a disadvantage at first, but it's actually very easy to implement by just dropping out this conditioning signal at a certain rate. So this is why we dropped out the text conditioning at this rate of 10% during the final stages of training the model. And to drop that out, you can just replace it with an empty string, basically. Here we see some examples of applying that classifier-free diffusion guidance formula. So the case S equals to 1 is basically no classifier-free diffusion guidance. It's just a diffusion model. And if we do that for this prompt, a professional photograph of a stormtrooper vacuuming the beach, we see that it does not really correspond to it. But we need to increase the scale to 7.5 here in this case to actually produce a crisp image, which also is aligned with the text prompt. Okay. And yeah, we can actually do more with these models than just text to image. So one application is inpainting, where we kind of take this pre-trained text to image model. So we now have this very general model, which can do text to image synthesis. We take this model and we can make it more specific. So for inpainting, we kind of want to fill gaps in an image. And what we do there is we simply need like masks or masked images and predict the missing regions. And we can do that by adding to the pre-trained model an additional input channel which processes these, or additional input channels which process these additional informations like masks or masked images. And because we have text control, we can actually specify what we want to have in like the output that we want to have in the masked regions. So we can make the leopard wear virtual reality goggles, or control the background with different text prompts, or place funny characters on this bench. Another application is what we call depth to image. This is also starting from a pre-trained text-to-image model. We then fine-tune this by adding this depth information as an additional input channel. So what this is useful for is that given such a depth map, which we can infer with a monocular depth estimation model, we can do structure-preserving text-to-image synthesis. So we can have like an input image, like this portrait of this man on the top left, infer the depth, which is the second image from the top left, and then condition on that and specify again with the text prompt what we want to have. And this works really well to preserve the shape and the structure. And another application is upscaling. So we can, instead of using this depth map, we can give the model a low resolution image during fine-tuning. This is also very easy to produce because downsampling is an easy operation. And yeah, again, because it's a text condition model, we can control the outputs through the text. So during upscaling of that cat here on the left, this is 8 times upscaling. We can either specify this to be a professional photograph or a digital artwork. Okay, and there's one more method that I would like to talk about that has been pretty successful with Stable Diffusion. And I also think that this method in particular benefits from being controllable through text. So Stable Diffusion cannot only be used to generate images from scratch based on text inputs, but it can also be used to modify given input images. And this is a feature that is known as image-to-image and is actually based on a paper that's called SD-Edit. And the key intuition of SD-Edit is to reuse the generative process of the diffusion-based generative model as is illustrated here. So given an input image like the sketch here, we add noise to it, and then we take this noised version of the image. It's not like completely noised, it's just partially noised, and then map it back through the decoding process of the diffusion model. And in this case, this model was trained on natural or like realistic photographs of churches. And this gives us a sketch to photo translation mode. And if we condition this, if we do this for a text-guided model, then we can actually specify with the text what we want to change in the image, but retain like the overall structure or the overall style. So I tried to sketch like this landscape here, and we can then apply this method and specify with the text prompt what we want to have in the outputs. So in the top row, I said, let's transform this into a fantasy landscape in the style of a watercolor painting. We can also do this as a kind of digital artwork training on ArtStation. It's the middle row, or specify a specific style in the bottom row. Yeah, and for me, as one of the developers of this model, it has actually been pretty surreal to see like the level of adaptation that has happened since we released the first version of this in August. And there are now so many different applications, web UIs, and new models that are built on top of the base model that I lost track of it, or somehow somewhat lost track of it. But in general, I think this is a sign of what I would call scaling creativity through open sourcing. So when we have a new technology which works sufficiently well and is being put into the hands of everyone who's interested in it, then we can get unexpected and new things, and development is very, very fast. And I just want to share a few examples of what I think are some nice applications, but there are way more, of course. So one that is pretty popular with Stable Diffusion is customized image generation. This is not restricted to Stable Diffusion. It works for any text-to-image diffusion model. So there exist different methods how to do that, but in essence, the idea is, let's say you have like photographs of your dog. And if your dog is not massively on the internet, then the model does not know anything about this dog. And then the idea is to use these few user-specified photographs to tune this object, like this dog, into the model, and then use the text-to-image capability to put the dog into new context, right? Like this dog here, swimming, sleeping in a doghouse, in a bucket, getting a haircut, and so on. This is a method that's called Dream Booth, but there also exist other methods. Yeah, and Dream Booth in general works extremely well with Stable Diffusion and can give results that are better than I initially expected. Especially tuning faces into the model is a very popular application. We also saw this with the Lensar app, which actually offers this as a service. So when they added Stable Diffusion, their downloads went to the roof for a while. It decreased again. Yeah. This is one that I like very much. It's objects taped to the wall diffusion. So someone used this to take a few photographs of objects taped to the wall and then apply this mechanism to have like a text-to-image objects taped to the wall diffusion model. Yeah, this is another nice application where people use this to upgrade or transform their child's artwork. This is based on image-to-image. I found this very cool. This is text to color palette with Stable Diffusion. So what this basically gives you, this has like the intermediate step of producing an image. So this is not like the full pipeline what we see here, but I think it's actually a nice idea because you can then specify color palettes based on emotions or something abstract like this. Yeah, this Stable Diffusion image-to-image was combined with other methods for video style transfer or style propagation. This one is called Synth, and produces results at quite a nice quality. There exist like countless plugins for user interfaces, also for Photoshop, GIMP, and so on. And a few papers actually came out and built on top of Stable Diffusion. So some papers interpret attention maps in the model. Another one that I really like is Instruct pix-to-pix. So this fine-tunes Stable Diffusion into a model that follows image editing instructions, which you give as a text prompt. So this means you have like an input image, and the model is trained to exactly follow these instructions, like add fireworks to the sky, or turn this into a still from a Western movie. I think this is a very nice application and shows like the potential of text-based conditioning. And then there are also other papers like this one, which exposed sketch guide as text-to-image. This works very similar to to the depth-to-image model or to the in-painting model, where you have like an additional channel which processes this sketch information. Yeah, and maybe to end this, I think this two-stage approach is more general applicable than just for image synthesis. So I think this framework can be interpreted as something where you can combine domain knowledge. In our case, the domain knowledge was about the high-frequency details of the images with a general scalable generative model. So other data types could be video or 3D structure or any other kind of structure. And if you have the domain knowledge and know how to construct such an autoencoder into an abstract latent representation, it should be easy to train a generative model, for example, diffusion model, but maybe a transform model on top of that representation. One example of that is this latent diffusion model for 3D shape generation from NVIDIA. There was one for structural biology, and one for symbolic music generation. So discrete symbolic music notation mapped into a latent space, into a continuous latent space with a variational autoencoder. And then the diffusion model is trained in a second stage. Yeah. Okay, so what's next? There are a few things which I think are very, very exciting. One is accelerating the sampling process to make this more like a real-time experience, because the diffusion model needs to be evaluated iteratively, many steps. It's kind of slow in comparison to, let's say, a GAN. And there exist methods. I had a chance to collaborate with Stanford and Google on this paper on progressive distillation, where we applied progressive distillation of diffusion models on Stable Diffusion and got it down to 4 steps, which is like a 8 times increase in sampling speed. There is, of course, video. So there's some work already on generating short video clips. And I think this will be super exciting going forward. Also because a video model might learn more general representations about the world than just an image model. And also generating longer videos than just a few seconds is like an interesting open question. Something that I'm also excited about is retrieval augmentation for diffusion models. This works a bit different from the standard training because during retrieval augmentation, the model actually has access to an explicit database of, in our case, would be visual instances like images. And the model retrieves, based on a text-image similarity, for example, instances from that database, which can help or guide the synthesis process. And I think this could be interesting for customization of diffusion models without requiring additional training. And it could also lead to models which are more efficient, because then the generative task is kind of to learn how to combine existing visual instances and just instead of learning everything from scratch. And then there's 3D, or text to 3D. Generating 3D assets from text would have like a massive impact, I think. There is some work already, which is super cool, based on using a pre-trained 2D, like an image diffusion model, to optimize implicit 3D representation, like nerves, to get a text to 3D model. And this is very cool to see that this actually works without explicit 3D data. And I think combining this with, for example, a video model, which would at least see multiple frames at the same time, would be a very nice way forward to improve the a few glitches that this still has. Okay, so that's basically it. Thanks to, or credits to like all my collaborators, Patrick, Andreas, Dominic, and Björn, and all the people who work on open source stuff. And I have a few resources if you're interested in that. There's this very nice Stable Diffusion online course with Google Colab notebooks, so you get a free cloud GPU. This is by Hugging Face, and it walks you through the individual components of the models. You can execute them with this in the Google Colab. There's the Stable Diffusion subreddit for very heated discussions. And yeah, there are lots of blog posts that try to illustrate this a bit more. So thanks.